Hello students, this is section 7.3, Proving Triangles Similar. Our learning goal for today is to use angle-angle similarity postulate, side-side-side similarity theorem, and side-angle-side similarity theorem. First, let's look at the angle-angle similarity postulate. It states that if two angles of one triangle are congruent to two angles of another triangle, then the triangles must be similar. So here we have triangle RST and triangle LMP. We have angle R congruent to angle L and angle S congruent to angle M. And we see a triangle similarity statement over here. Triangle SRT is similar to triangle MLP. Again, the tilde symbol is read as is similar to. So our first problem will ask us to use the angle-angle similarity postulate. And it says, are the two triangles similar? And if so, how do you know? At first glance, these two triangles look like they might be similar. They certainly share a 90-degree angle. However, we have to have two angles that are congruent in order to use the angle-angle similarity postulate. So here, since the 39 does not match the 51, we have to at least check the other angles to see if they match. So here we have 180, subtract 90. So that leaves us with 90, subtract 39. Takes 1 to get to 40, and 50 to get to 90. So here, by finding the third angle, we can see that we have two 51s, and we do in fact have two 90s. So are these two triangles similar? The answer is yes, and they're similar by the angle-angle similarity postulate. So let's take a look at two more triangles. Here we have two isosceles triangles. One of them has a vertex angle of 62 degrees. The other has a base angle of 68. So in this case, we need to show that the 68-degree angle could be one of the base angles here, or that the 62-degree angle could be the vertex angle here. So we know that this is 68 degrees. And some quick math here tells us that this angle has to be 44 degrees. Furthermore, some quick math with the triangle angle sum theorem tells us that these two base angles have to be 59 degrees. Since these two triangles, not only do they not share two angles, they don't share any angles whatsoever, so these two triangles are not similar. Our first theorem in chapter 7 is the side-angle-side similarity theorem. It states that if an angle of one triangle is congruent to an angle of a second triangle, and the sides that include those two angles are proportional, then the triangles must be similar. So much like congruence, side-angle-side works here as well. However, now, rather than the sides being congruent that include the angles, they must be proportional. Side-side-side similarity also works. So here we have, if the corresponding sides of two triangles are proportional, then the triangles must be similar. You'll get the opportunity to prove these two theorems in class in an upcoming day. So the second type of problem we'll see will ask us to verify triangle similarity. So here again we're asked the question, are the triangles similar? If so, write a similarity statement for the triangles and explain how you know the triangles are similar. Much like the situation we had with triangle congruence, we have a few options. We have angle-angle similarity, we have side-angle-side similarity, and we have side-side-side similarity. Since in this picture there are no angles given, it seems like the only option we have is side-side-side similarity. So let's pair the long sides. Let's pair the 9 with the 12. So I'll do the side from triangle ABC over the side from triangle EGF. So in this case we have 9 over 12. And the other two sides are congruent, so we have two isosceles triangles here. So we have 9 over 12 equals 6 over 8, which also equals 6 over 8. Since these two are the same, I can kind of ignore this second one. 9 and 12 have a greatest common factor of 3. So 9 divided by 3 is 3, and 12 divided by 3 is 4. So in this case, we get 3 over 4. 6 and 8 have a greatest common factor of 2. 6 divided by 2 is 3, and 8 divided by 2 is 4. These are the things that we want to match. Since the sides of these triangles are in proportion, we can say that they are in fact similar, and so we can write a similarity statement. In this case, probably the easiest starting point are the vertex angles of the isosceles triangles. So here I'll say that triangle CAB is similar to triangle GEF. And again, the reason that I know that is because of the side-side-side similarity theorem. So here we have another version of that same problem. We're asked to verify triangle similarity. We're asked, are the triangles similar? And if so, to write a similarity statement for the triangles and explain how you know the triangles are similar. So here again we have three options, right? Angle-angle similarity, side-angle-side similarity, and side-side-side similarity. So let's go ahead and separate the triangles from the picture. If we re-include the given information, here we have triangle ALW and triangle AEC. Both of them are right triangles as indicated in the original picture. A to L is 8, A to W is 6. The distance from A to C is the combination of two parts of 8, so we have 16. And the distance from A to E is 2 parts of 6, so we have 12. We have only a single angle, so angle-angle similarity is out, and since we don't know the third side, side-side-side similarity is out. It looks like if we're able to do this, it will be based on the side-angle-side similarity theorem. We have the included angle, so we need to show that the sides are in proportion. In other words, if we're to be able to say yes, and that triangle ALW is similar to triangle ACE, so we should be able to say that AL over AC equals the same thing as AW over AE. And in this case, by reducing both fractions, we can see that both of these fractions do in fact reduce to 1/2. So the answer is in fact yes. We have triangle ALW is similar to triangle ACE. That's our similarity statement. And these two triangles are in fact similar by side-angle-side similarity theorem. So proofs are back. If we want to prove that these two triangles, triangle ABC is similar to triangle PBM, given only the fact that segment MP is parallel to segment AC, it's important to remember what our options are. We have angle-angle similarity, we have side-angle-side similarity, and we have side-side-side similarity. So we're going to have to use one of those in order to complete this proof. So I'll complete this proof as a two-column proof. So again, we have statements and reasons. Our first statement, as always, is the given statement that segment MP is parallel to segment AC. And that is given to us. Seemingly the first step here would be to recognize that we have vertical angles. So in this case, I would say that angle CBA is congruent to angle PBM, and I would say that by the vertical angles theorem. So if I can show that only one more angle is congruent in each of these triangles, I can immediately go to the angle-angle similarity postulate. Conveniently, the Z shape that we see here, A to C, C to M, and then M to P, gives me something else that we've studied already, which is that these angles, angle C is congruent to angle M by alternate interior angles theorem. So now we can see we have one blue and one red angle in each triangle, and so therefore we can make our statement. triangle ABC, is similar to triangle PBM, and we're going to make this statement by the angle-angle similarity postulate. And that completes our proof. Finally, we're going to discuss the concept of indirect measurement. In this case, indirect measurement is the ability to find lengths that are difficult to measure directly. One method of indirect measurement uses the fact that light reflects off a mirror at the same angle at which it hits the mirror. This is known as the angle of incidence equaling the angle of reflection. So here we have Darius about to climb a sheer cliff face. He wants to know how far he's going to climb, so he places a mirror on the ground and walks backwards until he can see the top of the cliff in the mirror. If he wants to know the height of the cliff, he's using the fact that these angles, these 90-degree angles, and the fact that this angle relationship, the angle of incidence equals the angle of reflection, to prove that these two triangles are similar by angle-angle similarity postulate. Once the triangles are similar, all their angles must be congruent, and their sides must be in proportion. So since Darius knows his height, and he's looking to find the height of the cliff face, he can say his height is to the height of the cliff face as his distance from the mirror is to the distance of the mirror to the cliff. Again, here I'm going to use the trick of multiplying both of these by 2 to get rid of the decimal. So 2 times 5.5 is 11, and on bottom we get 2 times x. This equals 6 over 34. So using the cross products property, I have 2 times x times 6, which I'm going to write as 2 times 3, equals 11 times 34, which I'm going to write as 2 times 17. So here at least the 2's cancel. So we end up with 6x equals 187. Dividing both sides of this by 6, we find that x equals 31 and 1/6. So this cliff has a height of 31 feet, 2 inches. That concludes section 7.3, proving triangle similar. You now know how to use the angle-angle similarity postulate, and side-side-side similarity, and side-angle-side similarity theorems. Thanks for your attention. I'll see you soon.